So section 3.4 is about operational properties, part one. So the two main operational properties we're going to talk about this are the first translation theorem, which is a translation on the s-axis, and then the second property, which is the second translation theorem, which is the translation um, on the t-axis, which is related to Heaviside functions using unit step function, and of course, applications to solving differential equations with these new kind of functions. Okay, guys. Well, number one. So far, uh, we have uh, we have found the Laplace transform of some function f of t, which is going to give us some function of x, all right? But what if we have a composition function? Well, not a composition function yet. What if we have um, an exponential multiple of this function to transform? Well, that will result into a translation along the s-axis property here. Okay, so let's see what is that about? So here, let the Laplace transform of the function equal some function of a, and a any real number. So now we're going to find the Laplace transform of the product between an exponential function and another function, a polynomial, sine, cosine, etc. And all we're going to do is simply find the Laplace transform of the function the way we would usually do, and whatever we get as a function of s, simply shift it a by a unit, all right? So let's prove this result. So the transform of e to the at f of t, that equals the integral from 0 to infinity of e to the negative st times e to the at f of t. So combining, check this out, combining the not the fractions, the exponentials together, we would get the following: the integral from 0 to infinity of e to the negative s minus a t f of t dt. All right. Okay, guys, let me make a change of variables here. All right, let me make a change of variables. That'll be u equals to s minus a. All right, that's all I'm gonna do. So I'm going to replace this quantity s minus a with a u. That'll be the integral from 0 to infinity of e to the negative ut f of t dt. All right? But hey, isn't that the definition of the Laplace transform? However, instead of getting a function of s, what are we going to get? A function of u, isn't it? This would be f of u. But what was u? Isn't that f of s minus a? And this finishes the proof. Right? Well, you're not responsible to knowing the proofs, but actually how to use this. Okay, guys, before getting into the examples, it would be very convenient to use the following notation here, very similar to what we do when we are coming up with, what is that? Power series representations of functions, right? When I do this like u substitution, but in this case, I'm going to do s going to s minus a. I'm going to show you that in a second. How does that work? Okay, so evaluate each of the following plus transforms. So the Laplace transform of e to the 5t, t to the third power. So what I care here about is about a equals to 5. So that means I'm going to go s and shift it to s minus 5. All right. So here we go. So I'm going to, this is the same as saying the transform of t cubed, okay? And whatever we get after getting the function of s, replace that s into an s minus 5. Okay, here we go. What's the transform of t cubed? 3 factorial divided by s to the 3 plus 1. Evaluated at s going to s minus 5. Okay, 3 factorial, which happens to be 6. Okay, 6 over s to the fourth power, and then s goes to s minus 5, and this is 6 divided by s minus 5 to the fourth power. All right. Did we do something new? Maybe not much. It's the same formula for the Laplace transform, except that we are doing a shifting along the s-axis because it's the s, the one we're shifting. When we get to Heaviside function, when we take the inverse of that, we're going to shift along the t-axis. You'll see how that work is going to work. All right. Here we go. Okay, we're gonna find the transform of a combination of sines and cosines along with different power, different linear powers, more specifically of exponential functions. Okay, so yes, plenty of time. Okay, so here, uh, a equals to what is that? -2. So I'm gonna go s minus -2, which is s plus 2. All right. For the first shifting. For the second shifting, a equals to 7. That means s is going to go to s minus 7, right? That is this shifting here. Here we go. So this is what we do. Find the Laplace transform of cosine 4t. Whatever we get, shift the s to s plus 2 plus the Laplace transform of sine 3t. Whatever we get, shift the s to s plus minus 7, rather. S minus 7. I mean, the Laplace transform of cosine, the cosine is the one that has the s, right? So this is equal to, actually, let me make some room here. Let me make this a little smaller, okay? Because I'm going to need that space. So that is equal to s over s squared plus 16. But in this case, s goes to, what is that? S plus 2 plus 3 divided by s squared plus 9. But in this case, this shifting goes to for s to s minus 7. All right, let me highlight this. Check this out. Be careful here. It's every instance of s that gets shifted. Check this out. So this s going to s plus 2 gets substituted here and over there. All right, number 2. For the second term, s going to s minus 7. Well, we only have an s in the denominator, which is our s squared. All right. Just substitute and call it a day. So that is s plus 2 divided by s plus 2 quantity squared plus 16 plus 3 times s minus 7 squared plus 9. Final answer. And I think this is a good place to quit because the inverse transforms, those are gonna take a good minute to go. All right. So okay, let's finish the recording.